Well, dear student, now in this video, I will be explaining you vibration of stressed string. Vibration of stressed string, that is the illustration also of transverse stationary wave. Here this is a string of length L, stretched between 2 points. These 2 points you say any P or Q, A or B. It is under tension T. When it is plucked gently at center and released, suppose we pull it up and release, that is called, we pluck it at center gently. Then it come back and disturbance go this way and this way. The wave start traveling towards the fixed end, which are rigidly fixed. So the two ends of wire act as the boundary, and those waves which travel this way are reflected back, and two waves start traveling in the same bound medium in opposite direction, superimposing each other, produce transverse stationary wave. Since the rigid ends act as node, so in simplest mode of vibration, between two nodes at ends, there will be an antinode. This is node here, this is node here, this is antinode here. So if L be the length of string, the string may be a string of plastic thread, or maybe steel wire, or any material wire, or anything, but it should be in the form of string. Let's see. Then L is equal to lambda 1 by 2, or lambda 1 is equal to 2L. So if N1 is the frequency, so frequency excited in the wire, N1 is equal to B by lambda 1. We know in case of stretched string, the speed of transverse wave is given by V equal to under root T by M, or under root T upon pi r square D. D is the density or the radius of the wire. So N1 is equal to lambda 2L 1 upon 2L under root T upon M, or equal to 1 upon 2L under root T upon pi r square D. This is the lowest frequency. This is the lowest frequency. Lowest frequency of stretched string, and is called first harmonic. First harmonic, N1, 1 upon 2L under root T by N. Now if we plug it strongly, then it may oscillate with one or more nodes between nodes at two ends. In case there is one node, ये figure 1 scheme, ये wire, the same wire is there. Actually dotted line I have drawn here to keep the length same, to have assessment that length is not changed. In case one node between nodes at and lambda 2 is equal to L, so N2 frequency 1 upon L under root T by M. So you can add 2 upon 2L under root T by M. Twice N1. Second harmonic. This is called second harmonic, first overtone. Second harmonic. Second harmonic. And first overtone. First overtone. Similarly, the higher frequency which can be excited in the pipe, in the wire, are N3 equal to 3N1, third harmonic, N4, 4N1 is second overtone. Four N1, fourth harmonic. Fourth harmonic and third overtone, and so on. But generally, this actually along with this first harmonic, there may be any other higher harmonic also. That is why I told you we are able to distinguish between sounds of two similar organs. This frequency, fundamental frequency M, 1 upon 2L under root T by M. Here M is, what is M? M is mass per unit length. Mass per unit length. So not only length is consideration, tension and M also are criteria. Lesser the mass per unit length, higher the frequency. The child sound has higher pitch because mass per unit length is small, frequency is high. When he becomes a young person, then the mass per unit length of vocal cord increases. So frequency decreases, pitch becomes lower. I told you that the rolling of loin has very much lower pitch than sound of mosquito. Like that. So these are vibration of string. Now I am telling you something other which is not mentioned in the book also. Vibrations of rod clamped at center. Very cold here. Actually, dear student, listen me very carefully. It is a suppose steel rod or rod of any alloy, which is clamped at center here and put on a stand here. This rod of length L is clamped here at center. Now you may produce longitudinal wave by rubbing it along the length, or you may produce transverse vibration by striking gently it at right angle at one end. Here you can produce longitudinal as well as transverse wave. Longitudinal wave by rubbing it along the length. No. So vibration of molecules of rod will be along the resonance. So wave will travel this way. Here it is the rigid boundary. It will be reflected as well as transmitted. The wave produced here will travel through the rod, get reflected from here as well as transmitted through this. The ends are free. Center is rigid. So, in simplest mode of vibration, there will be node at center and antinodes. Antinodes at ends. That is like this. It will oscillate like this. So here L is equal to lambda by 2, lambda 1 by 2. It is the longest wavelength which can be excited this rod, whether transverse or longitudinal, कोई भी हो. So lambda 1 is equal to 2L. And you can use the formula for velocity of longitudinal wave, so V equal to gamma of y upon d. If you want to find out expression for frequency, by n बराबर b by lambda 2L. If it is longitudinal wave, then n1 is equal to 1 upon 2L under root y upon d. If it is transverse wave, longitudinal wave, or longitudinal waves. If transverse, then n1 will be 1 upon 2L under root P upon m, the same, mass per length. Now, if you produce higher harmonic, then the rod may oscillate like this, having here the node always there, at center node is always there. There may be nodes here also, and this may vibrate like this. But this will be the high frequency, but situation is here like this, कि higher harmonic disappear very soon. If anyhow you strike it strongly, then higher harmonic produced will disappear very soon. So this rod will oscillating only simplest mode of vibration. Now vibration of totally free rod. are at a place where there is no gravity, like in the satellite. This road is floating in satellite, and you strike it here, or you rub along this to produce, you rub it along the length to produce longitudinal wave. If you strike at one end gently, then it will produce transverse wave. Both can be produced here. I have told you that transverse wave can travel through solid only, while longitudinal wave can travel through all state of matter. Now its center also free. This is also free. So the center will also act as antinode. So vibration of this may be represented like this. We can represent the vibration of this rod like this. One node at center, here node and here node. This is totally free. Now if I bend this rod like this, but ends are free and center also free, then transfer vibration produced here, the rod may oscillate like this. And if I make it U shape, exactly U shape, so U shape, then it may oscillate like this. And like this. And this is the working principle of tuning fork. We fix a stem here. This is called stem of tuning fork. These are called forks. So frequency of tuning fork depend on elasticity of the material, mass and length. I have told you already. So this becomes tuning fork. Tuning fork. There is one device. There is one device here. This is called sonometer. Actually, sonometer is a device which can be used to illustrate the formation of transverse stationary wave and to verify the laws of vibration of stretch string. Sonometer. Sonometer. Simply, it is a box of wood like this. Having holes here in this box. Simply, it is a box. Here we fix support, two nails, long nails, and here a wire stretch here and passes over a pulley here, and we suspend a weight M. So tension in the string T equal to mg. That tension equal to mg. Now this wire passes over two bridges. Steel bridge, sharp edge. Then there is another bridge here. Steel bridge. The sharp edge, knife edge type of. So these 2 points will act as the boundary. When any vibration is excited in the wire, those vibration go into air and produce vibration, the sound, the whole system oscillate. Now suppose we excite, here we have tuning fork, this N. We put this vibrating tuning fork over this. I told you vibration are transverse, those transverse vibration produce wave which go through air into this, and each time produce oscillate longitudinally and strike the material and produce here vibration string. You know vibration of string simplest mode N by 2L upon M. T may be obtained from here. When length is small, frequency is high. Now, if we continue the tuning fork vibrating here and adjust the length of wire, here will be a meter scale from which we can read the distance between the two bridges or length of wire. So, by adjusting length, we can obtain that frequency of this length is equal to tuning fork. And when actually it will be applying periodic force and natural frequency of wire become equal to tuning fork, there will be resonance, a large sound is heard. Actually that sound is not heard in lab because of noise. So we put a ring here. That ring oscillate to and fro, or we can put here a piece of paper which is called rider that start jumping with large amplitude. Suppose then you have what? Resonance. So by measuring this length, noting this tension T and noting this mass per length, we can find out frequency of tuning fork. And if we know the frequency, we can verify that Kn proportional to 1 upon L. Smaller the length, higher the frequency. So you can read the book, and here M, I told you it is also under root T upon pi r square D लिखते हैं, और T upon pi square D 1 upon 2L under root stress upon density भी लिख सकते हैं, stress upon density. So this is simply the vibration of sonometer. In next video actually I will be taking numerical based on vibration of string, which have been general and in competitive exam also. I hope you will enjoy this topic very much and learn this. In every exam questions are asked from vibration of air core element string. Please like the video, share the video, ask your friend to subscribe my channel.